All right, welcome to this explainer on the hidden life of materials. Have you ever looked at a massive skyscraper or a jet engine and wondered how a block of metal is engineered to withstand all that extreme stress? Well, the secret doesn't lie in magic. It actually lies in the math of everyday phase changes. Today, we're demystifying phase transformations, and we're going to discover how these invisible, microscopic shifts hold the mathematical keys to engineering versatile, super-strength materials. Okay, let's dive into this. Think about watching ice melt into water, or seeing dry ice sublimate straight into a gas. We observe simple phase transformations like these literally all the time. But here's the wild part. The exact same thermodynamic principles that govern your melting ice cube also dictate the incredibly complex metallurgy of forging solid iron or crystallizing pure gold from a molten liquid. It is all the exact same invisible math.
So here's our game plan for today. We're going to start by exploring the power of phase transformations. Then we'll hit stage 1, which is nucleation. After that, we'll talk about overcoming the energy barrier, look at a really cool trick called the heterogeneous shortcut, and finally wrap things up with stage 2, growth and kinetics. Let's get into it.
Starting off with section 1, the power of phase transformations. If engineers want to control a metal's strength, or its hardness, or how much it can stretch, they have to intentionally manipulate its microstructure during a phase transformation. And this brilliantly illustrates how it works. It doesn't just happen instantly. It's a journey from the microscale up to the macroscale, and it always breaks down into two distinct stages. Stage 1 is nucleation. That's the birth of tiny, new phase particles, often literally just a few hundred atoms clustering together. Then we hit stage 2, growth. That's where those tiny nuclei start increasing in size, basically eating up the parent phase until the whole transformation is completely finished.
Which brings us to section 2, stage 1, nucleation.
So imagine the hero of our story, a brand new phase trying to form perfectly uniformly throughout a parent phase. Think of solid particles appearing completely evenly inside a cooling liquid. In material science, we call this homogeneous nucleation. But this new microscopic phase is facing an absolutely massive hurdle. It's fighting a thermodynamic battle, defined by a parameter called free energy, represented by the letter G. Basically, free energy combines a system's internal energy with its atomic disorder. And the golden rule here? A transformation only happens spontaneously when the change in total free energy is negative. Our little microscopic embryo needs that total energy change to drop below zero just to survive. It's a tough world down there.
Moving right along to section 3, overcoming the energy barrier. Now, what's really interesting about this is what happens as our tiny cluster of atoms actually tries to grow into a solid. It gets pulled in two entirely different directions by competing energy forces. On one hand, volume-free energy pulls it forward. That's what actually drives the transformation. But on the other hand, surface-free energy holds it back, because creating a brand new physical boundary between a solid and a liquid requires a lot of energy. Notice how, as the particle grows, the total free energy actually goes up at first. That initial peak is a massive activation energy barrier. If our little cluster of atoms is too small, it just shrinks and dissolves. It's essentially just an embryo. But if it can conquer that peak, if it hits what we call the critical radius, it becomes a stable nucleus, and the free energy finally plunges.
To put the sheer scale of this energy mountain into perspective, let's look at the math. To get the thermodynamic driving force strong enough to cross that barrier naturally, you have to drastically supercool the liquid way below its normal freezing point. Just think about pure iron for a second. Pure iron has to be supercooled a staggering 295 degrees Celsius below its normal equilibrium freezing point just to achieve homogeneous nucleation. That is a massive thermodynamic hurdle.
And let's put an exact, concrete number on this. Say we're talking about pure solid gold. Because of its lattice structure and that giant energy mountain we just talked about, it takes a cluster of exactly 548 atoms coming together to form a perfect critical nucleus just to survive. No joke. If only 547 atoms cluster up, nope, they dissolve right back into the liquid. It is literally a microscopic tightrope walk.
So you might be wondering, how do we actually help the phase change survive this tightrope walk? Well, we play with the temperature. By dramatically lowering the temperature, we alter the physics at play. You'll find that dropping the temperature significantly shrinks both the critical radius and the activation free energy needed to cross that barrier. We are basically lowering the mountain for our atoms. All right, section 4, the heterogeneous shortcut. Here's the plot twist. In real-world metallurgy, our heroic new phase almost never climbs that massive energy mountain all by itself.
So the crucial point is understanding the difference between our two pathways. As we've seen, homogeneous nucleation requires massive supercooling because of that huge energy barrier. But heterogeneous nucleation, that is nature's ultimate shortcut. Instead of forming out of nowhere, the new phase forms on pre-existing structural inhomogeneities, things like container walls, tiny impurities, or grain boundaries. By piggybacking on these structures, the new phase drastically lowers its surface energy. It essentially bypasses the mountain entirely, meaning it only needs a slight amount of supercooling to get the whole process started.
And that brings us to our final section, Section 5, Stage 2, Growth and Kinetics.
Okay, so once those stable nuclei finally form, they race to consume the parent material through something called long-range atomic diffusion. Basically, atoms physically migrate to join the new phase. Now, carefully follow how this delicate dance plays out across different temperatures. The overall transformation rate is actually a huge tug-of-war between the rate of nucleation and the rate of growth. See, at high temperatures, atoms are incredibly energetic and move fast, so growth is rapid, but nucleation is super slow. At lower temperatures, nucleation happens rapidly, but the atoms are way too sluggish to diffuse quickly, so growth plummets. The sweet spot? The overall rate peaks right in the middle, exactly where both of those processes overlap.
And this right here is exactly where the microscopic math translates directly into our macro engineering goals. It's pretty amazing. If engineers hold the transformation at a high temperature, they get very few nuclei, but those few nuclei grow rapidly. The result? A coarse-grained material. On the flip side, hold it at a low temperature, and you get millions of tiny nuclei that grow really slowly, producing a fine-grained material. They can even cool it so fast that it creates completely non-equilibrium structures. Simply by controlling the temperature, engineers dictate the actual grains of the metal, fundamentally altering its mechanical properties. Finally, we cannot talk about phase transformations without shifting our focus from temperature to the absolutely crucial dimension of time. We actually track how these transformations progress kinetically using the Avrami equation. This elegant little formula plots the fraction of transformed material against time, which gives us classical S-shaped kinetic curves. It's a perfect visualization for how transformations start off slow during nucleation, absolutely take off and accelerate rapidly during growth, and then gradually taper off as all the growing phases start crashing into one another. Which leaves us with this. Today we've seen how these phase transformations govern everything, from sublimating dry ice all the way to the high-strength steel beams holding up skyscrapers. By mastering these invisible thermodynamic hurdles, manipulating energy barriers, and utilizing the Avrami equation, we literally hold the keys to shaping the physical world around us. So the next time you marvel at a piece of advanced technology or a massive feat of engineering, ask yourself, how will you manipulate time and temperature to engineer the ultimate material?